This conference will now be recorded.
So, Deepa, so far we have covered a lot in this chapter, alternating current. Almost in the end, like at the end, we are now standing. So, in the last class, if you remember, we had discussed series LCR circuit, LCR. So, AC voltage applied to a series LCR circuit. So, that is what we had discussed last time. So, if you remember, this LCR circuit, we had got to know few terms like impedance, impedance. Okay, so that is denoted by Z, and this is equal to R square plus omega L minus, sorry, XC is XL means omega L, obviously. So this is inductive reactance and this is capacitive reactance. This is the impedance, and we have seen the amplitude of the current that is denoted by Im was written as Vm. We see voltage that is sine, so that is applied square and this. So again we have learned this thing omega, sorry, this chi L, that is omega into L. Okay, so is my voice clear and audible to you people so far? I'm just seeing a message that your network connection has been re-established, established, etc. So I just want to know, Deepa, are you continuously hearing me? Okay, I hope so. And see, Xc is capacitive reactance, which is 1 by omega c. So these are the terms we have learned already. So today's topic will be resonance in LCR circuit. Resonance. So this term is very much well known to you people because you have learned resonance of waves in 11th standard, right? Resonance of waves. So there are many instruments, musical instruments which acts on that. Okay, resonance. So basically, we have discussed in the 11th standard, or we have learned in the 11th standard, resonance in case of sound itself. Okay, resonance. Okay, so Deepa, are you not able to hear me? Guna madam, is it audible to you? Okay, I'll just check. Deepa, you can do one thing. You just uh, it, you just come out of the meeting and rejoin. Guna madam, is it audible to you? Am I audible to you? Deepa is saying that she's not able to hear me. Okay, I'll continue. I'm not getting response from your side. Okay, okay. So Deepa, you can do one thing. You just rejoin. You just come out of the meeting and then rejoin so that your voice, my voice will be audible to you. Yes, Guna madam, I have got your response. Okay. So today's topic will be resonance. So in 11th standard, we have learned resonance of sound waves. Okay. Mainly we have learned this. So depending on this, there are many musical instruments, and many other things are there which are driven by this resonance phenomena. Okay. So I'll see today in this LCR circuit, resonance in the LCR circuit is the electrical resonance. So our topic is today electrical resonance in this LCR series circuit. So whatever preliminary knowledge we know for LCR series circuit, like current, expression for the current, impedance, etc., we may be required, like we may require those things. So time to time we will recap and then bring into our use today. So first of all, this resonance phenomena is very much important phenomena in case of LCR series circuit. So what is this resonance? This resonance phenomena is very common in case of any object or any system which has a tendency to oscillate. Okay, if some system is there which can oscillate with certain frequency or particular frequency, so resonance is common phenomenon for any system which has a tendency to oscillate. Okay, that means resonance is being observed in those systems which has some tendency to oscillate. And see, when there is some tendency to oscillate, this oscillator or this oscillation has a particular frequency. So this frequency is called natural frequency of oscillation of the object or the system. Natural frequency of oscillation. I'll give you some example. So you have to remember that resonance is common phenomena for those systems which has a tendency, those systems which have tendency to oscillate. And while that system is oscillating, there is a tendency to oscillate in a particular frequency. That particular frequency is called natural frequency. Okay. Now, what is resonance then? Resonance is that if suppose an object has or a system has certain natural frequency of oscillation, and if you give some external force or external energy which has frequency near to the frequency of natural frequency of oscillation of the system, then the amplitude of the oscillation of that object or that system will be much more than earlier. I'll give you one practical example. See, there is a sweet girl who is swinging, and her brother, elder brother, is just pushing her with a certain frequency or certain period, I would say. So see, naturally this swing, because it has a tendency to swing, so naturally this swing has a frequency called natural frequency. If I say omega 0, suppose this is the natural frequency of oscillation of the swing. Okay, now what this boy is doing, actually he is giving a push to this girl with certain frequency, suppose omega, frequency of pushing. Now when this frequency of pushing is becoming nearly equal to omega 0 or the natural frequency, then we have this experience. What happens if somebody pushes continuously to us while swinging in a swing? What happens? We go much higher, right? The amplitude of this frequency, okay, amplitude of the frequency will be larger, very large. So large amplitude of frequency will be obtained. Amplitude of oscillation, that means the oscillation will be amplitude of the oscillation will be very large. So this experience, all of, I think more or less all of us has this experience. When somebody is pushing while swinging, we go much higher, right? Okay, our amplitude oscillation, amplitude of the oscillation increases. So this is due to the resonance phenomena. Resonance, so resonance, when the resonance occurs, the external frequency or the external source force or external energy, whatever we are providing to the naturally oscillating object, if the frequency of that push or pull or whatever type of forces you are giving, that becomes nearly equal to the frequency or natural frequency of oscillation of the system, then there will be resonance. So this resonance phenomena, we chemists and physicists, we use this resonance phenomena many places. So this resonance phenomena has much importance in science in many places. Okay, so I hope you have understood. See, there are few more examples of this resonance phenomena. See, if you have traveled by train, you might be observing this thing that while a train is just moving on the bridge, moving through the bridge, the speed of the train will be much lower. Why is it so? Because this is some bridge which was collapsed due to resonance. How resonance happens here? You know, if a train is just moving with very high speed, what happens? This breeze has natural frequency, as I said. So natural frequency of oscillation, that is omega 0, and the speed is such that gives another force of oscillation, like force or energy, to the breeze, which has again frequency some omega 1, which can be sometime nearly equal to omega 0. And at that place, like at this situation, this breeze will be oscillating violently, and the amplitude of the vibration will be such that it collapses. Okay, so that's why even in many countries, while there is a march by soldiers, their march also has been instructed to be in very mild way. Okay, while marching on the bridge also. Okay, so these are few phenomena of resonance. So resonance means when you give a force or energy by any external agency to a system which has particular natural frequency of oscillation. If the frequency of the external agency becomes nearly equal to the natural frequency of the oscillating system, then the amplitude of the oscillations increases like anything, and that phenomena is called resonance. Okay, that is called resonance. All right, so now we'll go to our textbook and see how do we analyze resonance. So you might be aware of this curve. Actually, this curve is, see, we have calculated for series LCR circuit, we have calculated the current, like I is equal to Im sine omega t plus phi. This is what we have found out, and we have seen that this omega, sorry, Im, the amplitude of the current, can be obtained by this formula. Okay, and we know what is XL and what is XC. XL is omega into L, and XC is 1 by omega C. This is inductive reactance, and this is capacitive reactance. This we had already discussed in the earlier class. Okay, now look, we are going to find out the condition for resonance in LCR circuit. Condition for resonance. So as we have seen in the previous examples, that the amplitude of the oscillations will be very large or the maximum at resonance condition. So in this case, you look, this is the current expression for the current. So when the current will be maximum, that is the condition for. So if we can find out the condition for this current to be maximum, then we know the condition for resonance. Okay, condition of resonance we know. So here you might be thinking, sir, how is it happening? Like how is the resonance happening here in LCR circuit? Where is the external agency? See, we have a power supply which is giving V is equal to V0 Vm sin omega t, this signal. So this signal has frequency omega, and this also has certain frequency. See, you can see the current, or LCR circuit, they have LCR, they have certain natural frequency of oscillation. When this becomes equal, then the frequency of LCR, natural frequency of oscillation, omega 0 becomes equal to omega, or some omega value of this oscillating voltage. Then there will be there will be a resonance in the series LCR circuit, and the current in that case will be maximum in that circuit. Current. So let us see how this current can be maximum. So if current has to be maximum, then this denominator has to be minimum. How is it possible? One way is there. If XL is equal to XC, that means this term becomes 0. Then your Z impedance will be simply resistance. That means your impedance is minimum. Then at this condition, when capacitive reactance is equal to inductive reactance, at that condition impedance is minimum, which is equal to the resistance of the circuit itself. Then look, the current Im will be maximum, and that will be Vm by R. Okay, Vm by R. And here resonance curve is plotted against the frequency, because the all frequency will not show you the resonance. So see, this is the frequency in the x-axis, and in the y-axis the current. And see, omega 0 is the natural frequency when my external agency, that means the signal frequency, is exactly omega 0. So at that condition, see, the current is maximum here. And if suppose in this case we have seen, so you can see the condition is omega L, suppose take omega 0 is equal to omega 0 C, that is the frequency where resonance happens. So this is the condition for resonance. So this is condition for resonance. Resonance. Okay, I'll erase some of the things so that this screen will be okay. Let me see. No, I don't have space. Next, I'll just erase all the things, and then I'll just keep the necessary things here. So look, we have condition for resonance. So that is omega L, omega 0, L is equal to 1 by omega 0 into C. That means omega 0 square is equal to 1 by L into C, which implies that omega 0. So angular frequency of, so this is the frequency of oscillation. Sorry, yes, this is the frequency where the resonance happens. Okay, where the resonance happens. So this is the angular frequency. You can find out linear frequency just by dividing this with, again, 2 pi multiply root over LC. This is F0 or frequency at resonance condition. So if the L means the inductor, this is the inductance of the inductor coil, and this is the capacitance of the capacitor coil. If these two are known, you can find out what is the frequency of resonance of any particular LCR circuit. So at resonance condition Z is minimum, that is equal to R. That means the circuit is purely resistive. LCR circuit behaves as a purely resistive circuit. Purely resistive circuit. Okay, resistive circuit. That means the whole power dissipated across the resistor, even if you have L, C and R, the whole power will be dissipated by or dissipated across the resistor only. And at resonance condition, the circuit becomes a purely resistive circuit. And at resonance condition only, the current will be maximum. So that is Vm by R. So this is the expression for the current. So sometime you will be given the voltage and you will be given the resistance and then self inductance value and capacitance value, and you will be asked to find out what is the frequency of frequency of resonance, what is the maximum current, etc. You will be asked to find out. Now look, this resonance, so the maximum current depends on then only R. If L and C are constant, that means your omega 0 is constant. Now if you fix L and C values and vary the resistance, see, as the resistance increases, the current also will be decreasing. Current will be decreasing because it is inversely proportional. I at resonance is inversely proportional to R. Okay, R means resistance of the circuit. Now there are two resistance values. See, for here one curve 1, R is equal to 100 ohm, and for curve 2 this is 200 ohm. So you can see the maximum value of the current is reduced by half almost. Okay, for one case 1 resistance is less, for case 2 resistance is more. Okay, and you know resonance curve with frequency is this is a typical curve. So this is a typical resonance curve. Typical resonance curve. Typical resonance curve. Okay, with frequency. With frequency. So it will give you a bell shape, almost a bell shape curve. Resonance curve means it will give you a bell shape curve. Let us just analyze few things about this curve. You can see this curve is a kind of bell shape curve like this. Okay, so this can be sharper, this can be sharper like this. Okay, what does this curve mean? See, this is the variation of this current with frequency. So at resonance condition, the current is maximum, that gives a peak. Okay, but as you go either way of the omega 0 frequency, suppose I take some frequency omega 0, maybe some 500 hertz. If I just take one omega, that is left hand side, that means suppose I take some 450 hertz frequency, and right hand side I take some 550 hertz. Look, the current is drastically reducing. Okay, reducing only at exactly at the omega 0, it has a large value, and on either side of omega 0 this falls very rapidly. Okay, so this is the typical resonance curve. So resonance curve means it will give you peak value or very large value at a particular frequency, whereas on either side of the frequency, the value of the current will be reducing very sharply. Okay, all right. So this is about resonance curve. So you might be thinking, what is the use of this resonance curve and etc. So or resonance etc. So why do we spend so much time to learn this resonance in the LCR circuit? Because it has applications in our practical life, where the application is, see, you can see the applications in, okay, so I should mention that this figures had been taken from website, so I apologize that I have not cited this. So in future we'll cite these figures, because I thought this is a very good figures, like these two figures are very good figures to uh, explain. So since this is a just teaching video, I would like like to take this kind of figures from website sometime to demonstrate these things. Anyway, so look, this is the practical applications we have. This resonance in the LCR circuit, series LCR circuit, is being used in our day-to-day life in case of TV set and radio set when we do some tuning. Nowadays, so this kind of radio is not available. Now radio, maybe you have some number 98.5, 98.4, 100.2, kind of those numbers. So those numbers are nothing but frequencies, okay? So FM radios nowadays, there are FM radios everywhere, and you get see radio jockeys, they used to say welcome to this 98.5 radio FM. So this is what? This is nothing but frequency. In earlier days, so what was there? There was a radio kind of this, where there used to be a knob. So this is a knob. Okay, this is a knob. So this is to be rotated. Okay, you need to rotate it and then tune a particular radio station to hear properly. So what happens actually? See, there are radio transmitters. There are many radio stations. They have their corresponding emitters. Radio waves will be emitted by those emitters. So these are called radio emitters. And this radio wave has to be, so that has to be accepted by the antenna, accepted by antenna. Okay, this has to be accepted by antenna. And what happens after accepting this wave by antenna? So this radio signal which is accepted by antenna acts as your signal voltage, like Vm sine omega t. So it acts as this. Okay, what you give in LCR series circuit by battery, it is obtained by this antenna. So this voltage, AC voltage, is obtained by antenna. So AC is in terms of radio wave. Okay. So after accepting this, in your radio there will be LCR circuit, series LCR circuit, as you can see from here. So this series LCR circuit, by just rotating the knob, what we do, we change, we change this capacitor, we change capacitance. Okay, capacitance of capacitors in series LCR circuit present in the radio. So when we change the C, you look, the frequency of resonance frequency of this circuit, this changes because we know this is root over LC. So this changes. So what we need to do is actually, by rotating the knob, we'll bring our natural frequency of oscillation of this LCR circuit, which is present in the radio, or in TV also earlier it was. So we'll bring that frequency of natural oscillation to a value which is a very much nearly equal to this frequency of the signal which is accepted by the antenna. If these two are nearly equal to each other, then there will be resonance. That means the current in the circuit will be very, very large, okay, for a particular radio wave. For not all the radio wave, for a particular radio wave which is emitted by a particular radio station will be clearly heard at a time. Why this happens? Because of the resonance. So I'll just summarize what happens in case of radio tuning. You have radio wave emitters. So there may be many radio waves emitted by emitters, and those waves will be accepted by this antenna, this radio antenna, and that signal act as your VMC sine omega t, that kind of signal. Okay, that means, in LCR circuit the battery gives the signal, but in this case the signal is obtained from the radio wave which is accepted by radio antenna. And after, so you can see that radio antenna, the frequency of that radio wave which is accepted by radio antenna has to be nearly equal to the frequency of natural frequency of oscillation of this LCR circuit which is present inside the radio. So that has to be equal to this frequency so that there is a resonance. And how do we do that? The tuning we do just by rotating the knob. So just by rotating the knob, what we do, we change the capacitance. We change this, we vary the capacitance. And because of that, the natural frequency of oscillation also changes. And by just adjusting the value of this capacitance, we can come to a particular frequency where the radio signal frequency and the natural frequency of oscillation of the LCR circuit present in the radio will be almost equal. And at that time, a particular frequency or radio frequency will be amplified in our radio, and we can listen very clearly to the radio station. So at a time, see, as you can see, the resonance curve, if your frequency is here somewhere on either side, the current is very, very less. So you cannot see, you cannot listen clearly. So radio waves which have, they can have frequency in all ranges, but your radio has to be tuned such that it satisfies the condition for resonance for a particular radio wave at particular time. Okay, so this is how it is applicable in our day-to-day life. Even in case of TV also, nowadays there are LCD screen, etc. So, and nowadays we don't use even this kind of antenna too much. Okay, so but anyway, better to know what is the application of this resonance phenomena in our day-to-day life. Okay, so now we'll see few more things. See, we have seen that the condition for resonance is x L is equal to xc. That means omega into L is equal to 1 by omega into c. So this is satisfied. So then what happens? The impedance become minimum. Okay, that is equal to R, and current become maximum. Okay, that current becomes maximum. That is Vm by R. So this happens. So in LCR circuit, So this is L, this is C and R. In LCR circuit, what we have seen that the voltage across L is exactly equal in this condition, resonance condition, exactly equal to VC but with the opposite sign, such that the voltage or the voltage across the inductor is cancelled by voltage across the capacitor. Okay, so voltage across the inductor is cancelled by the voltage across the capacitor in case of LCR series circuit at resonance condition. So to resonance happens, we need two components, that is L and C, for, like, this is necessary condition. This is a necessary condition that you should have in your circuit L and C. Otherwise, if you have only L and R, or only C and R, so these circuits cannot show or exhibit any resonance, because in that case, see, the voltage drop across L and voltage drop across R will be additive, nothing else. So in this case the current will be not maximum. In the CR case also the same thing. Unless this L and C are together in a circuit, there will be no resonance occurring in LCR circuit. Okay, so in electrical circuit. So this is a very important corollary, that in electrical circuit, if you want to have resonance phenomena, you must use L and C, inductor and capacitor, together in the circuit, such that your voltage across the inductor will be cancelled by voltage across the capacitor. Okay, so this is one corollary you should remember. Now we'll see what is called sharpness of resonance. We'll see what is called sharpness of resonance. So we have seen the resonance curve, that it is a bell-shaped curve. You can see that resonance curve. If you plot the current amplitude with respect to frequency, so this is the curve you get. Okay, see, this is one resonance curve, another resonance curve is this, another one is this. So all are resonance curve. But see, the maximum current is different for this and this. And also you look the shape of this all three curves. See, this has highest current amplitude and it is sharp. You can see sharp. Okay, it is not widely, the or the range of this is lesser than the lesser. Okay, so what I mean to say is that this curve is more sharper than the other curves. See, look, this curve, and even this curve. Okay, so sharpness of resonance means how narrow or sharp, how much narrow or sharp a resonance curve is. Okay, so that is the sharpness of resonance. So this, if I draw, so it is this is more sharper than this one. Okay, if I say this is the curve 1, this is curve 2, and this is curve 3. So curve 1 is more sharper, or sharpness of resonance is more in case of curve 1 than curve 2, and similarly sharpness of resonance of curve 2 is more than the curve 3, sorry, curve 3. Okay, so this is wider. Okay, this doesn't have. So when the peak is coming down and down, it is becoming more wider and wider. Okay, if the peak is more and more, or the amplitude of the current is more and more, then the curve is more sharper. Okay, more narrower. Okay, so this is called sharpness of resonance, and it depends. So if your L and C, L and C, if these are these are fixed, if these are fixed, then the sharpness depends on R. So if your R is more, then sharpness is less. That means, we know this Imax current, maximum current is Vm by R. Okay, this is what we know. So if the current is just reducing, then it will be wider in the frequency side. Okay, just to maintain its maximum, just to maintain its constant area under the curve. Okay, so this Vm by R, if your R is more, then your sharpness is less. You can see here, see R1 is greater than R2, then greater than R3. So this is a typical curve which is actually being asked in many places in many competitive exam. So please remember this. What is sharpness of resonance, and this is the curve for different resistance values. The sharpness is different. Okay, sharpness is different. Okay, so this sharpness of resonance can be defined by a mathematical formula that is omega by omega naught by 2 delta omega. So this is mathematically defined as sharpness of resonance. So sharpness of resonance is defined by this particular term. Okay, measure of. So this is kind of measure of. This is a measure of sharpness of resonance. Okay, and there is a mathematical formulation of this sharpness of resonance for LCR series circuit. So we'll just take up the resonance curve. You see here, if I consider two omega values, one is omega 0 plus delta omega, that is on the right hand side, somewhere here suppose, or sorry, somewhere maybe somewhere here. So look this place omega 1, and another frequency omega naught minus delta omega, which is in the left hand side at the same place, actually symmetric place, left hand side omega 2. So this omega 1 and omega 2 we have to define first. How do we define this omega 1 and omega 2? We define first that your I max, the maximum current, sorry, the current in the circuit becomes 1 by root 2 of the maximum value. So I define two frequencies on either side of the resonance frequency, omega 1 and omega 2, where the current becomes 1 by root 2 times the maximum current. Okay, this is what we take. So then power dissipation will be half of the maximum power dissipation in the circuit. at resonance so at this condition where at these places, okay, omega 1 and omega t, so not exactly at the resonance frequency. So if we take these two, then you look omega 1 minus omega 2, so this is called bandwidth, and this is given by 2 delta omega. Okay, 2 delta omega means difference in, see, this is 1 delta omega and this is another delta omega, the spread of, so delta omega means the spread of frequency around the resonance frequency, spread of frequency around the resonance frequency is called delta omega, and 2 delta omega is called the bandwidth. That means, see, you might have experienced while tuning a radio, see, when we are not exactly at the resonance frequency, but we are just little bit away from the resonance frequency, we can see various sounds, we may be able to hear sounds of the same radio station, which we can see clearly, we can hear clearly at the resonance condition. We may be able to hear in between this range 2 delta omega, we can hear the sounds or broadcast by that particular radio station in between this range. This is called bandwidth, but our sound quality will not be very, very clear if it is not exactly at the resonance condition. Okay, so this is called bandwidth. So if you set a frequency anywhere between this 2 delta omega or bandwidth, you may get to listen some sound from the particular station, which you can listen very clearly at the resonance condition. Now if you do little bit of mathematical formulation which is given in the textbook, in your ncert textbook, if you do very carefully these calculations, you will eventually arrive to the value of delta omega. So our attempt will be to find out what is delta omega, and we know omega 0. So we have to find out sharpness of resonance omega 0 by 2 delta omega. So this is the measure of sharpness of resonance mathematically. So our aim is to find out what is delta omega. So for that we have first taken these two, chosen two frequencies, and then we'll be putting in this, okay, in the condition where the current is becoming 1 by root 2 times the maximum. So that condition will apply, and if you do bit of calculations, then we will be eventually arriving what is delta omega. So these are the equations numbers, you can just follow this. I'm not just going to detail calculation of this, so that's why I am showing you here. Now if you get this omega 0 by 2 delta omega is easy to get, okay. So omega 0 by 2 delta omega you will be able to get as, so this is actually for a series LCR circuit, this is omega 0 L by R, okay. That means if your frequency is large, so sharpness is depending on three factors or three term or three parameters. One is omega 0, that is the natural frequency of the system itself. You can just leave that. So one is L. If your L inductance is more and more, your resonance will be, sharpness of resonance will be more and more. If your resistance is more and more, sharpness of resonance will be less and less and less. So that we have seen in that case, the curve will be flatter and flatter and flatter. Okay. So there is another term which is called quality factor. Quality factor. So this is also an important term because there are questions in the competitive exam from quality factor as well. So just go through this. The quality factor is defined by this one, omega 0 L by R. Omega 0 L by R is defined as quality factor. Okay. So omega 0 L by R is defined as quality factor. So what is the relation between quality factor and sharpness of resonance? If your quality factor is more, your sharpness of resonance is also more. Okay, sharpness of resonance also will be more if your quality factor is more. So you learn few terms here. So natural frequency, bandwidth. Then we have learned here what is called sharpness of resonance, which is denoted by or defined by omega 0 by 2 delta omega, and quality factor, which is defined or denoted by Q, that is omega 0 L by R. Okay, so this is all about sharpness of resonance. Okay, one more thing, I just want to deliver one more point, that is, see, to emphasize that we need both L and C in the circuit to get resonance. That is one point. Another point, at resonance condition, the circuit is purely resistive. Purely resistive. Okay, that is R. That means the whole power will be dissipated by whole power will be dissipated by R or across R. Across R at the resonance condition. Okay, we'll take up few numerical examples on the next class related to LCR, series circuit, and resonance, etc. Okay, so today I'll stop it here. Once we go for the application part, then you will enjoy this topic again. Okay, so I hope you have enjoyed it, but this will be again enjoyable when we go and solve numerical problems using these concepts. So next day we'll take up few numerical problems on this particular chapter. Okay, and then we'll finish the chapter. Okay, all right. So bye for today. This is all for today.